I want to do some, okay, maybe this was a bit quick, so I wrote some things to maybe make this clearer. So this is a notation, poly2C2 is just homogeneous degree 2 polynomials on 2 variables. So it's spanned by x squared, xy, y squared. Okay, and so it's in 2 variables because this vector space has degree 2. Okay, so you can evaluate them everywhere on this vector space. And now this vector space's degree is of dimension 3. So if you do a poly2 of poly2C2, you would have to have degree 2 polynomials in 3 variables because this is a 3-dimensional vector space. So you get them in 3 variables and they correspond to the coefficients of your polynomials here. Okay? And so this is a tiny bit of more complicated computation where you don't just flip x and y, but this is where you replace an x by an x plus y. And now if you do that, so x goes to x plus y, x squared then goes to x squared plus 2xy plus y squared. So this is a very suggestive way of doing it, and this is the canonical way that works. Right? And if x squared goes here, then see a is the coefficient of x squared, right? So you identify x squared with a, and you identify xy with b, and y squared with c, and then you get this equality. So this is how it acts. And then you can now see how it actually acts on a squared, and you would expand this, but I was, there was no time. Okay, so this is good. So this is how this action works. This action is a canonical action. It's the action that just defines actually the discriminant. So it is the case that the discriminant, you see, b squared minus 4ac, if your matrix G has a determinant 1, then b squared minus 4ac is fixed under this action. So you have this discriminant polynomial, and this is the unique one. So this is a 6-dimensional vector space. It has a unique vector that is fixed under the action of a special linear group. Okay? This is the action that defines the discriminant as its invariant in this vector space. And so the goal is to study these polynomials. They are like the discriminant that can be used to separate points from orbit closures. Right? So that is the goal. And now this action, what does it actually give us? So why would we care about this action now on this space of these functions? Because it gives structure to this space of functions. We already see that you have this action and it identifies the discriminant. Right? It's the one unique SL invariant. And it does more things like this. So this action gives you much more information than just identifying the discriminant for you. Yes? Yes? This is I defined an action on this space. Yeah, an action is a group morphism from your group to the. You can define but there's only one way of actually properly define. So a group element acts, and the action itself is the way of how things act. Okay, so it's a group homomorphism. Okay, so now you can apply any 2x2 matrix to any vector here in the 6-dimensional vector space. Right, and something happens, you get some other vector out of it. So your 2x2 matrices move your vectors around, and the discriminant is fixed under the special linear group, and so the general linear group just rescales the discriminant. So so much more is true, and I want to just say that. Yes? This one here? Why I've written this? It says that if you apply a 2x2 matrix, so G being a 2x2 matrix, you apply to the discriminant, then you get the discriminant back, but it's a rescaled version. So you get just the determinant squared, and that's a computation. No, that is not how I define it, but this is an observation that you get if you do the calculation. So if you now plug in a 2x2 matrix with having 4 different entries, alpha, beta, gamma, delta, and you apply this here, and you expand everything and see what happens, then you get exactly this vector back, but up to a scale that was the determinant of this alpha, beta, gamma, delta matrix squared. But this there are several ways of seeing this, but the one that I presented here is you could do a thing like this and then see what happens. Right? So there's I do the calculation also in the lecture notes. There's a calculation, but it's a bit messy. There are probably more clever ways to see this, but this works for every polynomial in every way. You can always do this kind of calculation. So why is this now interesting? Because so whenever you have a I want to define. So I want to define what is a representation. You have a finite dimensional vector space, and this is what poly. Yeah, I want to define what's a representation. So main example being poly d, poly n c n squared, say, and it's a representation of the general linear group. So in a representation, is actually a pair V and rho of a finite dimensional vector space V and a group homomorphism. Actually a linear it's a representation, a group homomorphism. And the group homomorphism goes from G, from your group, whatever your group is, to GLV. And it's a bit confusing because our group is always a general linear group. So you always have a general, so we started with a GL2, and you map it to some, it says that you have a group element and you can apply it to a vector in your vector space. And formally what you do is you have a group homomorphism that sends your group element to some element in the general linear group of your vector space, and that's what you can apply then. It's a map, right? It applies, you can now apply it. So it says that you have some rule that tells you how to apply a group element to your vector space, to elements on your vector space. Like here, right? Like this one here. And that's a representation. And a sub-representation is something that is a linear subspace that is closed under the group action, okay? And we already seen this. So example of a representation is poly d, poly n, c n squared is a representation. Well, we are only concerned with the general linear group here. So poly 2 c2 is a representation. Right, these are all representations out of GL, in this case of GL2. And now there's a sub-representation in here that is spanned by the discriminant. So b squared minus 4ac is also a representation because you apply to it some matrix from the GL2 and you stay in this linear subspace. Okay, so this is called a sub-representation. And in general, if you have a vanishing ideal of a variety, and now this is our important sub-representation. So you take a vanishing ideal. So say I of x is the set of P such that P, if you evaluate it at any point in x, is always 0. This is an ideal, is a vanishing ideal. And in our case, this is graded. Everything is still things have a degree. So then a natural thing is that the homogeneous degree D part of your vanishing ideal actually lies in, well, those are some polynomials. They are homogeneous of degree D on wherever so say X is a sub-variety here of poly n c n squared. Then this is actually a sub-representation. So this says the following. So the statement says the following. It says that if you find a function that vanishes on X completely, then you can apply actually this action of this group, and this still vanishes on your variety, and follows from general principles that this is the natural thing that you would define. So, but this gives now structure to the set that we want to study. Note, this is precisely the set that we are really interested in, because if we want to separate a point from X, proving a lower bound, then we take a function here, we take some element of this ideal, and we evaluated our point. But now this has a lot of structure. It's actually a sub-representation. And the sub-representation always decomposes some nice way. So you'll always have that okay. Okay, so those are sub-representations. Now everything decomposes actually in terms of sub-representations further and further until you cannot decompose it any further. Okay, you find some sub-representation, then you take that vector space out, and there's a natural way of defining an inner product so that to take the orthogonal complement is still a representation. So you can decompose the orthogonal complement further, and you can decompose all parts further, and you get a nice way of decomposing your whole vector space into parts that are called irreducible. Okay, so V is called irreducible if it has no non-trivial subrepresentation. So it always has a zero vector space and itself, of course. So, for example, poly 2 C2 is not irreducible because it has some subrepresentation sitting here. But this representation is irreducible. It's one-dimensional. It cannot have any one-dimensional. It cannot have any non-trivial subrepresentation. It's a linear subspace whose closed under the action of the group. It's this action. Yeah, here it's exactly that. Here the action is precisely just you scale everything with a square of the determinant. Yeah. Yeah, so this is the one action here. This is always how it's going to be. So this is the canonical action here on that space. And all subrepresentations all the time is this one. It's the one that describes the discriminant, and it's precisely the correct action. And so now you say, okay, so these are irreducibles, and everything decomposes into irreducibles. So GL, say capital N, is reductive. And this means that every representation, every GLN representation, so also poly D, poly N, C, N squared, for example, is a main example, decomposes into a direct sum of subrepresentations, of irreducible subrepresentations. Okay, and so in our case, this would be, there's this subrepresentation and its orthogonal complement is 5-dimensional, and that 5-dimensional one has to check is also irreducible. So that one has to check, and the action, but the action is this action here. So it decomposes into these two parts, and it's a direct sum of these two. It's a 1-dimensional and a 5-dimensional vector space. And okay, and now what? It is known, so these types, these irreducible subrepresentation is exactly known how they can look like. So there's this 1-dimensional vector space with the determinant squared, but it is precisely classified of how these things can look like. And they are given by partitions. So the isomorphism types. So yeah, okay, so you'd say V and W are isomorphic. And then this is what I mean, that you know how they look like, isomorphic. If there exists a vector space isomorphism, say phi, that has that phi of GV is equal to G of phi V. Right? So you're acting on the vector and you map it, or you map it and then you act on the vector. So behaving, V and W behave exactly in the same way. Also with respect to the group action, you're acting on V or on W, doesn't matter, you can go back and forth with your vector space isomorphism at any point. Okay, so then they are called isomorphic. And now your natural question is, so what are the building blocks of every irreducible GLN representation? And they are completely classified, it's known how they look like. And this 1-dimensional and this 5-dimensional block, they have a name to attach to it. And those are given by partitions. So the isomorphism types of irreducible GLN representations are given by partitions. And partition is just a list of numbers that's non-increasing. by partitions lambda, and lambda is just lambda 1, lambda 2, up to, in this case, lambda capital N, and you just have the property that lambda I is greater or equal to lambda I plus 1. Yeah, in our, I'm a bit sketchy here because you need the irreducible polynomial, but I don't want to talk about that at the moment. Yes. I of x is a subrepresentation. X has to be a variety that has a group action on it. So it must be, for example, it could be a group orbit closure. It could be anything. It could be a set of polynomials of complexity at most k. But then your complexity measure must respect the base change. So base change should not change the complexity. So. Yes, this is precisely so. And you would take border complexity, and then it's fine. Yeah, and you would do everything homogeneous, but that's basically then yes, that's exactly your x, and you want to separate a point from that, precisely that. And now yes, and now everything that vanishes has now a very nice structure. Yeah, you can use. You don't have to do determinants here. You can use. Yes? Completely, yeah. This is completely, yeah. So only acts is using the fact that you are using the determinant. Yeah, so the rest of the structure is completely universal. And, yeah, it's studied independently, right? It's by mathematicians completely independently. So, okay, so those are isomorphism types. I want to say one thing about them, so I have to be a bit shorter than I planned to, but I want to say one thing about these types. So if you find an irreducible representation, it has one vector that is called a highest weight vector, that I want to still say. So so let me call them, so maybe they get a notation. Let's say V lambda, okay? And we do know how they look like, but it just takes some time to explain. Okay, we have a completely explicit combinatorial realization of how these things look like. There's this nice tableau combinatorics. But so you can ask me, I'll explain to you. So there's V lambda, and V lambda contains, so every V lambda contains precisely 1 up to scale, contains a line, basically contains a highest weight line. And that is contains a line of highest weight vectors. So a highest weight vector is the following. So a highest weight vector has the first property is that upper triangular matrices do not change your vector. And the second is, if you take diagonal matrices and let them act on your vector, it rescales your vector like a discriminant in the following way. It rescales them so the lambdas give you the exponent vector of the rescaling. Okay, this is the one vector. This is always one vector like this in there. So, for example, the discriminant has the property that if you act on it with a matrix like this, its determinant is 1, so it fixes the discriminant. And it also has the property that if you scale it with some matrix, like if you act with a diagonal matrix, well, I mean, since the determinant of an alpha 1, alpha 2 matrix is alpha 1 times alpha 2, it's rescaled by alpha 1 squared, alpha 2 squared times f, right? So this is how it's rescaled. So it's a highest weight vector, and this lambda is exactly its type. So it lies in a, so we conclude the discriminant lies in a V22, right? This is what we conclude. It's somehow lying in some representation. It is highest weight vector, so we conclude that b squared minus 4ac lies actually in a V22. It satisfies precisely the properties that I wrote down there. And the other thing is, in our setup, if you look at a squared, that's also a highest weight vector. One has to check upper triangular matrices fix a squared in this model. And if you act with diagonal matrices, then the a, this is just and lambda 1 is 4 and lambda 2 here is a 0. So the A is scaled by an alpha 1 squared, and the A squared is rescaled by an alpha 1 to the 4. So this one lives inside a V40. Okay, and so we see, and this is a 5-dimensional vector space. From general principles, there are formulas like a hook length formula tells you this is 5-dimensional. So we can write poly 2 C2 decomposes as a V22 plus a V40. This is how it decomposes, and it's still so. In the vanishing ideal now is also so. You have say X is your Waring rank 1 polynomials. Then in degree 2 is a subrepresentation. It's just a V22 because there's just a discriminant in there. Okay, so that one, the other one does not vanish, right? So therefore, it's just a V22. Yes, A squared is the highest weight vector. Those are not. Yes, because of upper triangular. Yes, you chose a. Yes, you can choose this a bit in a different way. So highest weight vectors, you actually choose which one. I mean, so it's not. This is not a very canonical choice to choose kind of upper. What does upper triangular mean? You basically choose an order of your basis, and then it's only unique up to it. Yes. So you can also define what is the coordinate ring, and the coordinate ring is defined, say in degree D, is defined as exactly the polynomials. In our case, it's like this: poly n cn squared, and you mod out the vanishing idea in this degree. So it's the functions that live on your x. Okay, so you don't care if a function is 0. You might add or subtract it arbitrarily to whatever function you have. So you only care about functions on x. So you can equivalently you can think of you have a polynomial, but you only care about evaluations on x. So you restrict its domain of definition to x. That's the coordinate ring. And here we see this is also as a representation. You have this representation is poly 2. In our case, in our example here is the coordinate ring of x. In our case, would be you mod out. So you have the V22 plus V40. You mod out the V22. So you are still there with a 40. All right. So this still survives. So it works out really nicely. Everything fits together like this. Okay. And the conclusion is the following. So this is the conclusion I want to draw, and then I want to say a tiny bit about the slides that I have. Okay, so first of all, if you want to know how often one remark, if you want to know how often do specific types appear, this is called a Prahladhism coefficient. So if you are given a D and an N, and say this is some number, it doesn't really matter, and you are giving a type here, some partition, so these basically you get 4 inputs, and you want to now know how often does a specific type appear in my decomposition. That has been studied by mathematicians. It's called the Prahladhism coefficient, and we don't know we don't know if that map is actually in sharp P. It's an open question. So what does this coefficient count? So again, as an input, you get a D and an N squared, say, and also a lambda, and you want to know a natural number. How often does it appear in my decomposition? That counts something, but we don't know if that's in sharp P, because these computations are very, are expensive. So we don't actually know how to count this properly. There's an open problem. It's problem 9 in Richard Stanley's list of open problems from 2000 about positivity and algebraic combinatorics. Right? So these things are very classical and studied, but many open questions. But now let me draw a conclusion about lower bounds, and the conclusion is now the following. Okay, so you want to separate x from a point. But now, so you find f, and f is 0 on whole x, okay? And f is non-zero at your point. Then what you can do is, okay, f is in the vanishing ideal, but my vanishing ideal splits into this direct sum of parts, okay? So this means that f is actually a sum of whatever, some finite sum of fi's. And each fi lies in some V part, some irreducible, where the Vi is irreducible. Is an irreducible representation. And this means that that means that you must find and those Vi are not only irreducible representations, they are irreducible representations in the vanishing ideal. Right? So they all vanish. So this means all the Fi's vanish independently. But since F does not vanish on P, there must be one of these Fi's not vanishing on P. Right? So we find there exists some I such that Fi on X is 0, completely 0, but Fi on P is non-zero. So this means already we conclude you can prove a lower bound by picking not any polynomial F to separate. You pick a polynomial in an irreducible representation. That's enough, right? You can just restrict yourself to searching for polynomials in irreducible representations. And even more is true. So not only that is true, these Fi's come from an irreducible representation. But this means that since there's a unique highest weight vector in these representations, see Fi now comes from an irreducible representation, say it's Vi, but so how does it look like? So Vi is actually, every vector in Vi can actually be written as some matrix G, say Gij, and you take a highest weight vector and you call it, I don't know, say you call it F, capital F maybe capital Fi. And capital Fi is the highest weight vector. Vector in Vi. Okay, and now if you look at what happens if you take the highest weight vector and apply all the different matrices to it and take its linear span, that's a representation for sure. But since this was irreducible, it must be the whole representation. It cannot be some sub-representation because this was irreducible. And this means that you get every vector by just applying some matrix to your highest weight vector and take the span. Okay, this gives you immediately every vector. So this means also that you don't have to actually look at every Fi in some irreducible. You only have to look at some translates of highest weight vectors. So as a conclusion, there exists a highest weight vector. So if P is not in X, then there exists a highest weight vector F in some irreducible representation, say call it V, such that F vanishes on the whole X and F is non-zero, but not at your point, so you have to do a tiny translation at GP for almost all. That's a tiny technical constraint for almost all G, but you can take literally any random will do. Okay, that's the conclusion. And I have another 15 minutes, right? 15. So so therefore, I think I have to go to the slides. Otherwise, this is I want to say something a bit more, but maybe let's do it on the slides, if that's possible, to switch to the slides. If that's possible. If not, I can just, so maybe let's just, okay. So this gives us a strong restriction. I mean, we can now search for highest weight vectors and they will vanish on our variety X, right? So those are the things that one tries to study. And one can define, for example, there could be several highest weight vectors. Ah, very nice. So do I have, I can press here, right? Good. Oh, perfect. Okay. Yes, okay. So let me just go, this is some introduction. Let me go to somewhere where it's interesting. So here, okay. Okay, so the general setup is we have some orbit closures, say this is capital X, and we want to separate a point P. And now we make actually an observation, so we can do with highest weight vectors. But what one interesting idea is to do this not just with highest weight vectors, but with some. So highest weight vectors will always work, right? This is a theorem. But now the idea is to have a slightly coarser look at things and only count the number of appearances of certain irreducible representations. So that's a slight, I mean, maybe maybe this works or not. So we will see. Okay, this doesn't, okay, here is good. So a point is in this orbit closure, say this is our set X, if and only if the whole orbit closure of your point is contained in your orbit closure, because the orbit closure is the smallest set that is closed under the group action, also topologically closed. But now you are comparing two varieties here, X and Y. Now you're not having your, so now I'm sorry that X is equal to, whatever is X here is Y here. This is the problem with slides, okay? But let's see. So this is just your usual, okay, so you have a comparator of two varieties. We discussed this, not in this language, but we see the discriminant, and this is what we had on the board about the discriminant, right? And we have the ideals, our subrepresentations, and we can define these quotients are the coordinate rings. That is exactly what we did. And now, this is now interesting. Assume now, for the sake of contradiction, that one variety lies in the other. Now, this is an approach to separating, okay? So then you find a surjection of functions that are defined on Y, and if you restrict that domain of definition just to X, it's a surjection, right? And such a surjection by restriction implies that if you just, that these multiplicities, which are defined in a second, this multiplicity here will exceed the multiplicity here. And the multiplicity is, you count the number of occurrences of these irreducible types in your representation. Here, for example, the multiplicity, I can write it like this, the multiplicity of 2, 2 in the vanishing ideal here of x2 is 1. Okay, I just count how many appear, and that's so just counting that. And it turns out that if you have a surjection, then you get an inequality of this type. Right? So everything works nicely. So this means that if you find a lambda where you have more on the x side than on the y side, then x cannot lie in y, and it's called a multiplicity obstruction. And if you even have a 0 here, then then this is called an occurrence obstruction. Okay, and now about these types of obstructions, there were some questions. Let me go back. Yeah, let me go back. So we proved that you cannot have occurrence obstructions in the for determinant versus permanent. And so Scott Aronson asked actually whether all the separations that we could have with multiplicity obstructions could also be obtained with occurrence obstructions. And it was a bit interesting question, because if this would be true that you always could do it with occurrence obstructions, then this would show that you can also not have multiplicity obstructions here. But indeed, all these works before where obstructions were used, where multiplicity obstructions were used, they all were done also by occurrence obstructions. So now what we went out to do is we wanted to find out if this was a thing, or if one could, if there were natural group varieties where one could actually see that this is not the natural behavior. Because intuitively, and from some suggest that these occurrences are much weaker than these multiplicities in general. And this is the paper. The paper constructs a natural setting where you can actually separate with multiplicities, but you cannot separate with occurrences. And gives also some way of handling multiplicities and computing these multiplicities. So that is the contribution of the paper. It's a setup, and I'll show you that setup. It's two varieties. It's not determinant and permanent. It's much simpler. It's about factoring power sums, which should not be possible. So if you have a power sum, that is usually it doesn't factor, right? But let's look at the two varieties. So one variety has this interesting CH. It's called for chow. It's called the chow variety. It's just the variety of products of homogeneous linear forms. So you have homogeneous linear forms. You take their product. That's a variety here. And the other one is the polynomials of border warring rank at most k. So you just have linear forms. You raise them to the nth power. You add them up, and gives you some variety. Okay. And now a natural question would be, is actually not the question that you would think. So therefore, we look at whenever do these power sums can be written as a product of linear forms. And there are not so many cases where this is possible. So this is one case. L1 squared plus L2 squared factorizes like this. And you can do this also if more generally, if you only have two summons, then you can do this in a higher generality. But these are rules of unity. It's not that, so it just says there are some trivial cases where yes, the power sums factor, but usually for any non-trivial setup of parameters, they don't. And this is also known, right? And we wanted to now, since these multiplicities are very difficult to compute, we want to have some easy setup. Maybe we can prove this even with some obstruction, right? Should be very easy. And indeed, this can be done. So you can do, this is your lambda, it's n squared minus 2 n 2 is your very specific lambda that you pick. And for that lambda, we can show that the multiplicity here for the variety of products of homogeneous linear forms and the power sums is actually, there's a difference between the two. So this means this is a multiplicity obstruction. And we also show that not in all cases, but in some finite cases, we can actually rule out that there are occurrence obstructions where we show that whenever the multiplicity on the power sum side is positive, then it's also for the product of homogeneous linear forms. So this is not an occurrence obstruction. There cannot be any occurrence obstructions. So okay, and the reason. So why is this now? Why do we think that before all multiplicity obstructions could also be obtained by occurrence obstructions? So before it is that many of the multiplicity obstructions in low degrees are actually occurrence obstructions. If you are in very low degree, then it happens that you, as we saw, as we saw here, that there are no multiplicities here. There's a 2, 2, there's a 4, 0, and nothing appears twice. Right? And if you're in low degrees, this happens. And so if you only study the low degrees or whatever your computer can do, you will not find multiplicity obstructions. And so now these parameters here are chosen carefully so that they are large enough so that you have no occurrence obstructions, but they are small enough so that you can actually compute these numbers. What's happening with the mic? I'm not. I can just ignore the microphone. If it's fine for you guys. Okay, so this is carefully chosen. I mean, if you make it too large, you cannot compute anymore. If you make it too small, then everything will be obstructions. And so multiplicity obstructions. How do you prove that there's an inequality between these? This is actually a nice step. So the other step is done by computer calculation. That's a non-trivial computer calculation, but maybe this is the more interesting part, and that I will, in the last 4 minutes, maybe give you a glimpse of what kind of properties we use to actually show an inequality between these things. Yeah, it's good.
Close the button.
Sure. All right. It's good. Test. Yes, good. So this will be interesting for the people who are actually post-progressing these videos to actually put the sound together, I guess. But okay. Okay. Good. So we try to prove an inequality here between. So between the proof works, first of all, so we saw this is now a note for the plathism coefficient, is the highest multiplicity that you could expect. D poly NCN. So it's the highest multiplicity that could possibly be any of these coordinate rings, because coordinate rings are quotients of this, right? So this is the multiplicity that appears here is the plathism coefficient, is the highest possible number you could possibly get. And we get that we max it out on the right-hand side. So this is the highest multiplicity that you can get. And it's a proposition that we proved earlier in this paper with Burgesser and Panova, that, so if your k is large enough, it maxes out this multiplicity. In other words, you can so this is in different words. If you look at the set, this variety here, this is an infinite, well, it's in variety, it has infinite many points, but it's a hitting set for homogeneous degree less or equal to k polynomials. So those polynomials cannot distinguish, right? So if these polynomials vanish on the power sum variety, they are 0. Okay, so this is good. So this is maxed out. So what about that? So it remains to show that this is smaller. That it somehow doesn't max out, and it doesn't. So we use an inheritance theorem to say that the multiplicity that appears on the tau variety, this variety is actually, you can replace it by an orbit closure of just the products x1 up to xn. This is almost the same setup. It's an inheritance theorem. I don't want to go into the proof right now, but it's an inheritance. So this is products of homogeneous linear forms. These are also products of homogeneous linear forms, just more variables. But it gives you the same multiplicities. And look at rational functions here on the orbit, which are more functions potentially than on the orbit closure, because what you allow is you allow the same functions, but now you also might have poles at the boundaries. So this gives you potentially more functions. And these are things that one can have a handle on. So there's an inequality because you're now allowing, so the notion here is a bit misleading, because this is not a quotient. This is not defined as a quotient. This is the same symbol, but it actually is a set of rational functions on this set. Right? It's not a quotient like this all the quotient things are defined. This is a new different object here of functions where you can also define a multiplicity. And for this one, we can actually study the multiplicities in a nice way. By a series of applications of theorems, we can actually relate it to precisely just the dimension of some invariant space. So here maybe let me not go into the details because there's no time, but you can compute these multiplicities by basically taking an irreducible representation, like this 5-dimensional thing, and then there's a group, which is H, which is a stabilized point of x1 times xn, and you take invariance in your irreducible, you take invariance with respect to that stabilizer, and you count so the dimension of that space. And that gives you one of these multiplicities. And so here's the stabilizer of this point. So the product x1 up to xn, so what does it stabilize? So you can multiply it with a diagonal, you can act with a diagonal matrix where the product of the alpha i's is 1, or you call it qn. And you can also, this is a semi-direct product with a symmetric group, you can also exchange the different variables, right? It also doesn't change your polynomial here. So you can rescale a bit, but if you cancel out the rescaling, you can exchange. And now, so the only thing to do to compute this upper bound here is to compute, so by this line of theorems here, to compute the H invariant space in your V lambda. V lambda being precisely the thing we constructed over here. And it's a two-step process. You take first the Qn invariance, and then you take on the Qn invariance the Sn invariance. And you get some nice combinatorics happening. If you want, for example, look at the Qn invariance, then what it counts is the number of semi-standard tableaus of a specific shape lambda. I mean, I didn't introduce, but it's a nice combinatorial notion. You count objects here. And now you go to Sn invariance, and you get some new plathism coefficient here. And note, so it's a bit subtle, but this is a lambda dn, and this is a lambda nd. So this is exactly flipped, okay? So this is a coefficient. This is non-trivial that happens here, but you get a coefficient that is flipped here. Let me now tell you what is to be shown. So, okay, we still want to show this. The multiplicity here is actually upper bounded by this alpha a lambda nd. So if that is smaller than a lambda dn, then we proved this fact, right? So we have to prove that this, if you flip the two, then the coefficient decreases. That's what we have to show. And indeed, it can be done. So you can, if you take this specific lambda, then you can show there's a difference of 1. And this has been shown using symmetric functions. You can, I mean, these are classical notions. You can express these notions in terms of symmetric functions and do exactly compute this difference. And this is possible because this is very close to only having 2 entries. So the third entry is very close to 0, it's only a 2, so it's still manageable. So for 2 entries only, those are the 2 row partitions, we know precisely what happens. And now if you change it a tiny bit, you get some pretty long calculation to reduce everything to 2 rows, but in the end it turns out that this is 1 plus. So the difference is exactly 1. So we found that by computer search, we found the conjecture that this should be a difference of 1. And then we did calculations that this is indeed 1. Proof this is 1. new and gives a new case of what is called the Fox Conjecture, where the Fox Conjecture says that if you flip D and N, then there should always be an inequality between the two. And there's always, if the larger one is the left coefficient, that should be the bigger number. And if the, like here, this is the bigger number than here, because the n plus 1 is larger than the n. This is a conjecture. It's called Fox Conjecture. It proves it in a new case. And here, this finishes completely the proof, right? I mean, let me maybe just say again. So the multiplicity here is the first step is an inheritance theorem to some orbit closure. Then we have an inequality between that comes from looking at rational functions on the orbit, which can be by a line of theorems. We've seen that this is a flipped Plathism coefficient, which then is actually equal to, which is strictly less than the Plathism coefficient by a symmetric function argument, which we know by this multilinear algebra inclusion-exclusion that this is equal to the coordinate ring, to the multiplicity on the power sum side. And therefore, this cannot be embedded. And so this is a way of using these, and those are not occurrences, and one can show. So this is just a computation. So for this one here, we use a property here. For example, we take all these generators of the semigroup. So these are basically triples where the coefficient is actually non-zero. And we computed all of them, and there are not more. So you can by some easy little program you can write that these generate that these are enough to check if you want to prove these multiplicities are positive, then you only have to check it on a finite subset. Because you can always, if a multiplicity is positive and some other multiplicity is positive, then the multiplicity with respect to their sum is also positive. And this means that this gives you a semigroup of these take the semigroup and show that this is true for all. And we just constructed by computer and the larger case as well. And summary is, we show it by multiplicities. We use a relationship between orbit and orbit closure, and we show it. We show that there are no occurrence obstructions by multiplicity obstructions. We verified that there are no occurrence obstructions. And I don't present the last paper here. The last paper is about a tighter connection between the orbit and the orbit closure. So here you see there's some upper bound given by this rational functions here, and it's a bit unsatisfying that you only have an upper bound by this multiplicity, and there's no way of going in the other direction. So there should be a tighter connection between two, and the second says that there's a tighter connection between these multiplicities here on the right side and these on the left side. And it's a master's student who's doing these studies with me, and we do this for the power sum, and we show that you get a squeeze type of theorem where you have this multiplicity is bigger than that multiplicity, and then we get some other multiplicity, a third multiplicity coming from the bottom, and it's very much related to this multiplicity here. So we get a third multiplicity that comes from the bottom so that we can squeeze, so we get a better handle on these multiplicities, because it's unsatisfying to only have an upper bound. And that is with my student Kandasamy, but I'll not go over that, because there's no time. I'm out of time, right? This is exactly out of time. Good. And then there should be a last slide that says thank you, I guess. I don't know. I just scrolled through this. There. That is for, so that paper says it for occurrence obstructions. It's only, we do not know the multiplicities there. They are very hard to compute. So we'd only know for, so it's probably possible to show that it's not only do occurrences not work, but also if you insist on the multiplicities on the one side being very, very low, then it's probably also not possible. So that is probably also very, sorry? No, well, that is true, but no, but I mean, so they were both very far from zero. So occurrence obstruction says one drops to zero completely. So so here everything was very close to actually to maximal. So I think the paper where we show it's no occurrence obstructions work, it also shows that if one of the multiplicities is very, very low, then it also doesn't work. But they're both very high. Yes. And also there's an issue, so we use crucially in that paper where there's no occurrence obstructions for determinant permanent, we use crucially that the model of computation was a model where you have a polynomial and project with affine linear forms. So if you replace that with a homogeneous model, like an iterated matrix multiplication of homogeneous linear forms, there's no no-go result of that form. Right? It's very important, and for the whole construction, it's very important that we have affine linear forms. It's crucially using a result of Haddish and Lamberg that only works in this padded setting. And I don't have any conjecture. It might be the case that occurrence obstructions even work in a non-padded setting. I would not bet on that though, because this is a non-padded setting here. The two varieties, nothing is padded, everything is homogeneous, and still occurrence obstructions do not work. So they might just not be a way to go. I think this is how it looks like. That occurrence obstructions, you get them if your degrees are very low. Then instead of multiplicity obstructions, they are even occurrence obstructions. But that's more of a coincidence because you don't have many objects floating around at that point, right? There's only so many lambdas that are, and then you get occurrence obstructions. But there's no reason also why there should be occurrence obstructions. While there are papers by Larson and Pink and Yu that actually say something about multiplicities and say that you can reconstruct from the multiplicity data, you can reconstruct the stabilizer and things like this. So there's much more hope that you can go further with these multiplicities instead of looking at the occurrences, yes. It might be that you require some other techniques for studying these. I mean, here was very nice that we used an upper bound. You need some kind of upper and lower bounds, maybe some approximation techniques, anything. It's not so clear. Most of these things are known to be sharply hard. For many of them, it's open how hard they are, but they look pretty difficult to compute. And yeah, so some kind of approximation. I mean, even a theory of how difficult it is to approximate these numbers would be nice. There's nothing like this. There's nothing like this. These coefficients, I mean, these Plathison coefficients, they appear in these lists of open problems, of fundamental open problems. But then textbooks, for example, don't often cover these coefficients because there's not so much known about the coefficients. The deep theory is missing, so then they appear in these lists of open problems. But then there's an algorithm. There is algorithmic treatment, but not by computer scientists. So for example, there are a lot of algorithms that do kind of computations like this, but I think none of them has a runtime analysis, for example. Right? This is the state of the art. There's a lot to be done still, I think. Oh, I'm not aware of that, actually. The question was that instead of just asking for is the power sum, does it factor? You asked, does it maybe have two summons that factor? And I think that is not such a common question that I don't think was asked so far. It would be interesting, definitely. So the question was asked basically in terms of people study, is the polynomial irreducible? That's what they do. And then they say, oh, it's irreducible, and then it doesn't factor, and that's kind of the reason why. But then this question is much more difficult if you allow two summons, of course.